another more interesting topics in Python, which is on simulation. Okay, so you take attendance. Hopefully that attendance could be taken later if you if you have not taken it. Okay, for the latecomers especially. Okay, so I'm going to adjust my screens nicely. Then we can begin it. Okay. So we just take a look at the coursework. So you'll find out that I just uploaded. This is not assignment 10. I think it's assignment 11, if I'm not mistaken. Okay, so let me check. I think there are 2 assignments. Okay, so let me see this assignment 10. What is it? Is it assignment 10? Or is it assignment 20? So I got confused. Okay, and this one, is it the same or is it a repetition? So this is assignment 10. This is another assignment as well. No, not be opened. Well, anyway, I have prepared the assignment for you. I'm going to check the assignment to see whether there is any mistakes in that. So this is 4K. This is a repetition, if I'm not mistaken. Okay, this. Okay, so I think it's a repetitions. So I'm going to remove one of the assignments. So we have only assignment 10. Okay, so let me remove this. Maybe I'll remove this one. Okay, so we are going to look at a new topic which is on part 3 simulation. So you click on this simulation. You'll be able to go to this collab again. It's a bit slow on my laptop. You can use Google Lab to open this instead of downloading it. Okay, so you click on the Google Colab and please run the script on the screen instead of running it on your local computer. Okay. Okay, so there is a few numbers of simulation I want to show you. Example, first example, 2 example, 3 example, and then so the idea is to show you the simple way to simulate the evolutions of a physical system that evolve under the physical law. Okay, so we have seen, for example, we have a pendulum. Right, the pendulum will swing according to some equations, and you solve the equations. The solution is in the form of a sinusoidal function. So the pendulum clock will change, and the angle will change as a function of theta. So at t equals to, as a function of time, sorry, at time t equals to 0, it is at some location, and when time is 1 or 2 or 3 or 4 or 5, then the location will be at different places. So participants, anyone who wants to say anything to me? So I'm waiting for you. If you have questions, you can raise it here. If you don't have any questions, you may want to switch off your mic. I think someone's mic is on. Yongwei, is it his name? Yeah. So Yongwei, yeah, you switch off your mic already. That's fine. Okay. So the idea is to make use of what we call the parametric equations, right? So I keep on telling you about the parametric equations. Remember, parametric equation is a set of equations that dictates how the x and y coordinate of a function change with time. Now, in a sense, say for example, maybe this is not a good example. A better example would be the pendulum. Okay, the pendulum is a good example of a parametric equation. So you look at this example, the simple harmonic oscillator. X is a function of time, right? So when t changes, the angle theta will change, and then the angles would cause the position of x coordinate and y coordinate to change. Right? So x and y that is shown on my screen here refers to a set of parametric equation. T is the parameter, x and y refers to the coordinate. So if you are given a set of parametric equations for the coordinate x and y, then when t changes, then the position of x and y changes. So you can easily simulate the locations of the coordinate x and y at different time. Then you overlap them on the same spot on your screen. Then what you get would be an animations in forms of a video. So when we say simulations, we are referring to the process of displaying how the physical systems changes with time in the forms of a video. Now the difference between the animations and the simulations is quite subtle. I would define simulations to be an animation which is based on a set of physical equations. So the animations that is in the forms of a video is, sorry, let me say it again. If you're doing a simulation based on a set of physical equations, then that animations is real in the sense that it is evolving according to the law of physics. So if you look at cartoon, right, you know, like cartoon that people now, these rabbits like just drops into the air from still, and then when it drops, the speed of this dropping is not very natural. So if you watch movie, if the movie is simulated without any simulations, so let me admit people coming in first. Okay, fine. So let me say it again. So if a systems evolve according to a set of equations, then the motions looks real because it's evolving according to the law of physics. So if you watch a movie, for example, if the movies have a lot of animation, for example, Spider-Man, right? Spider-Man jump from here to there in a tall building. Now, if the simulations is not done based on the law of physics, then when you look at the animations, it looks like it's very fake, right? It doesn't look like it's real. Okay, so we learn a lot of physics. We learn a lot of equations that could be written down. Then this equation governs how the object will change with time. So if you were to use that equations to perform the animation, then I call that a simulation. The simulation based on physical law. Now, animation that is not based on physical law is just animation, it's just like cartoon. Okay, maybe if you want to make it as real as possible, then you should animate the movement of the object based on physical equations. So we have seen many equations that change with time, that dictates the positions of the object change with time. So pendulum is this. Okay, so this is another example. I think this is another example. Let me see. A projectile motion. A projectile motion is an object that is thrown into the air at some initial angle. Then it will fly through the air and forms a parabolic equation, a parabolic pattern that looks like this. Okay, so you want to simulate how the ball should change with time, right? So you want to see how the ball changes with time. So that is also animations. Now the other thing is the wave, right? The wave is the most interesting one. I think the wave is the here we got a wave. So I got two waves. I think we got two waves. Why we should put two waves? There should be only one wave. Okay, so I think that is a repetitions. So the wave that is being shown here is a wave, pure motion of wave. So let me check again. Okay, so I think this is a repetitions. So maybe I should just remove this part. I think this shouldn't be here. Okay, so let me remove this. Remove this. How could I remove this? I remove this. Maybe I just remove it from. Yeah. Okay. Now people are coming in, so let me admit people. If you come in late, then I have to spend time to admit you. If you come in earlier, then you would not, sometimes distract my attentions. Okay, so let me look at my simulation here. Simulations for this part should be thrown away. Okay, so this part should be thrown away. Okay, so let me save it. Okay, so then you should see better. Okay, so let me start off my simulations and my explanations. Before that, I would like to save a copy for this. Save a copy. Save a copy so that I only modify my modified copy, so it won't affect the content that you see on the screens online. Okay. Okay, it's the same thing. Okay, so we are going to simulate a few examples like wave, right? So we are going to see how wave changes with time, and we're going to simulate, for example, how an oscillator pendulum, single pendulum, change with time, and then we also want to see how the projectile motion looks like when you simulate it, and also we want to simulate a box, okay, a box of particles. Maybe I just run it and see whether you can see. So this is the particles in the box. When you run it, why is it doesn't run? Okay, so you see that the box is there, it's fixed in the same plane on my screen, and you see that the particles of this is moving around. Okay, when it hits the wall, then it bounces. But the effects of the simulation is not that good, like it fickles a little bit. So we're going to learn how to do that kind of simulations, and also we can do something more fancy. For example, give me a set of parametric equations, or give me equations that control how the coordinate of the points changes with time. Right? So once you have that equations, say for example, have equations that describes say a triangle that looks like this. Not a triangle, this is not a triangle. Say you have a pyramid. It's a pyramid, is it? Yeah, it's a pyramid. Not a pyramid. You have a triangle in a circle, and you know each of the points is located on the triangle, on the circle. Then you make it rotate, right? So you want to simulate the rotations of a triangle inside a circle. Now, how you do that? Now, the idea is you have to first know the coordinates of the points, and then you need to know how the coordinate changes with time. So you need to have an equation that tells you how each of the coordinates changes with time. Then you displace the points at different time. Then what you will see would be a simulations of an object which is rotating. Okay, I think it is rotating. I'm running it again. Now sometimes it takes a bit of time for the simulation to come out. Sometimes it doesn't come out for some reasons. So if it doesn't come out, then what you should do is to restart the kernels again and then run it over again. Okay. I think this is Python is relatively weak in doing the simulation. Maybe I'm not good at the simulation part. If someone knows how to do a better simulation using Python, then that would be good. I think there's a specialized packages just for simulations, but the simulation I'm going to teach you here are simulations which are of a simple type. It will not be very fancy, but it's just sufficient to displace the animations on the screen. I think that is what we do here. So the kernel is restarting. The people are coming in again. Okay, so you can see that this is a triangle that is rotating. So what I'm doing here is I'm changing the coordinate at the different of time. So I need to know how this coordinate changes with function of time. Okay, so I'm telling you a few examples here. Not to mean to bore you, but I want to show you the similarities in all these simulations. Now, these simulations of whether it is a pendulum or whether it is a 2D dimensional projectile motion or whether it is a wave, right? So all of these has a commonality, that is, these simulation systems changes with time. So you need to know how the coordinates on your simulations change with time. So you need a function like this. For example, you need a function that tells you what is the values of the wave. Now, y is the y values of the wave. That wave has values of displacement called y. Right? So at a location x at a particular time t, at that particular instances, in that particular instance of t, and in that particular location x, the values of y, which is the values of the wave at that point, is that much. Right? So you need to know how the amplitude, well, not the amplitude, how the displacement of the wave at x and t changes as a function of time, as well as, in this particular case, as well as x. Right? So as long as you have these equations, then you'll be able to tell the values of y at different x and different t. Now this is a sort of like a parametric equations in a sense. So once you are given this parametric equation, then you can always easily simulate it. Right? So what you can do is that you can plot the graph of y as a function of a sine kx minus omega t plus phi for t equals to 0. Right? Then you display the profile of the function y. Then you change the t to say 1 delta t. You have to define delta t to be a slight change in time. Then you display again the profile of the functions. Then you change the time again to another delta t, and you display it. So you display it many times. Then what you see on the screen is a different profile that appears at different time. So when you overlap all these profiles together, then you have a video. I think the idea is quite simple. Okay. So in order to do that, you need to use this additional. You need to do this additional thing called IPython. I think you can only do the simulation and display on the Jupyter. If you are using Spider, probably it may not work. I have not tried this, but probably it may not work. So you need to use a Jupyter, and then to import from IPython, which is a package for the display package. Then you need to clear the display and do a wait there. So you need these two important steps. Then after you clear the display on the screen and wait, then you have to sort of like prepare a screen for display. Then you do the plot, but the plotting has to be done repeatedly in a loop. So you have to put up a loop that changes in time. Right? So time equals to 1t, 2t, 3t, 4t, 5t. So at different values of t, you always clear and wait on the screen, then call the display, and then print the plot on that display. So in the next t, the display will be cleared and prepared, then you plot it again on the same display. When I say display, I mean locations on your screen at the same place. Okay, so that is a simple way to understand it. Okay, so let us do it one by one. The idea is very simple. And let us try to simulate a profile of a wave. Now, before we do the simulations of the wave, it is very, very important that you understand what you mean by wave. In your Form 5, okay, so you study, in your Form 5, you study wave. In your 103, you study wave. In your matriculations, also you study wave. Right? Wave is described in 1D wave, which is called a 1D pure sinusoidal wave. Is simply a functions that changes at different location, t, and time. So a functions of a wave is given by this. But what I'm trying to do now is to explain to you, for those who do not really understand what wave is, each of the symbol that is expressed on these equations has a meaning. Now you have to understand each of these symbols. Like for example, y represents the displacements of the wave. So for example, wave is like you have a sound wave, right? Not a sound wave. Now is not a good example. So you have a string. A string, you stretch it, right? So at a particular point along the string, that point is given by x. Like x tells you which is the location of the point on the string. T of course is time. Then at that particular point of x, if you displace it a little bit, that displacement is y. So y here refers to the displacement of a stretched string from its equivalent position. So usually the y here is generally the values of the wave. In the case of a stretched string, y is the displacement. In the case of a sound wave, this y refers to the compression value of the air. And then for example, in the case of a pendulum, then y refers to the displacements from the equivalent position in terms of the angle, okay, or in terms of the displacement position from the equivalent position. So anyway, y is the value of the wave at different locations in space and at different instances in time. The values of the wave is different. Okay, so you have different. Well, you have the coordinate of x, then time changes continuously. So the wave in this case is sort of like form of field. Okay, field means it is a value that could be found on every point on space. At different time, the values of the field could change. Okay, how would this field or the wave change? It change in a simplest manner for a one-dimensional pure sinusoidal wave. It changes as a function of a sinusoidal function. So here A is the maximum displacement in the wave value. K is a constant that dictates the wavelength. So K here refers to the wave number. It is equal to 2 pi over lambda, where lambda is the wavelength, and omega is angular frequency, and phase is the phase. Okay, the phi is the phase. So a single pure one-dimensional pure sinusoidal wave is characterized by, most importantly, two quantities which are independent from each other. First quantity is the wavelength. Equivalently, the wave number. The wave number and the wavelength are equivalent. Okay, when you say wavelength, you are referring to lambda. When you say wave number, you are referring to k. But k and lambda are related. The other very important quantity is the frequency. Right? So frequency could be expressed in terms of just the frequency f or angular frequency theta. Okay, so angular frequency is omega, f is frequency. Okay, so you either describe the wave in terms of its frequency or in terms of the angular frequency omega. So frequency and omega are simply written by this. F equals to 2 pi omega. Yeah, I think so. And then you can sometimes need to know the period. The period is just 1 over frequency. So all these are basic quantities that describes a one-dimensional wave. Okay, I think there's hardly any other kind of wave that is simpler than a one-dimensional sinusoidal wave. Okay. And then when the wave is moving, like when you have a wave, one-dimensional wave, you see it moving, right? So the speed of its move is given by omega over k. So in your 103, you're supposed to learn how to derive this formula, right? So you know the wave is changing sinusoidally and it appears to be moving along the x directions. How to derive the speed? So it is given by the omega dt, and for this case there's no omega change and there's no k change, so it happens that the speed of the wave is given by omega over k. So this formula only works for one-dimensional sinusoidal wave. In a more complicated situation where you have your wave is not sinusoidal but say a group wave, then V will become d omega dk. So anyway, this is a simple case. These are all the important simple characterizations of a wave. So wave is a constant, depends on the frequency of the wave and also depend on the wave number of the wave. And then if your wave number k is reverted, then the wave will move in opposite directions. Okay, so for example, if the k is this, so k may be say 1, then it moves in the right direction. If you make k to become -1, it will move in the opposite direction. So a wave also has associated values called phase number. The phase number determined by the initial conditions. So you have two waves, and these two waves initiated at different instances. Say for example, at t equals 0, the first wave is initiated and it starts to move, but then wave 2 would be initiated only say after 0.1 seconds. So that wave number 2 is slightly slower than the phase 1 in terms of its initialization. So these two phases would be different by a phase. Right? So this is a very important idea of the phase. So these are all the numbers that describe the phase, but the most important thing is that the frequency and the wavelength. So you either express a wave in terms of kx minus omega t, or in terms of the wavelength and the frequency. So either one will do. So usually we use this, but you have to understand the relationship between k and lambda, omega, and f. Okay. So lambda is very simple. Okay. So then we have to decide how to describe the simulation. It's very simple. So I think I can reproduce these things here. Okay. So maybe let me cut and paste all this stuff first. So let me prepare all the Python packages that is required. So I need a matplotlib to plot the graph, and I need this to get all the numbers of pi and whatever, and then I need to plot it. And I also need to use this later on. But for this moment, I would not use this because I'm not going to show you the simulation. I'm going to show you how to perform the simulation step by steps. Okay. So first of all, you need to have a functions. Say y is a wave function. So y is a function of x, and then it also emits a function of t. Okay. So there are many different ways how we do it. So your wave has to be y equals to the value, which is given to be a times sine np sine. Wait. So it's np sine, then times k, times k times x minus omega times t, omega times t plus 5. Okay, so this is the formula for the phase, for the y. Then you say, okay, return y. So this is how you define. But in order to print out the values of y, there's the phase, the wave. You need to specify the amplitude, you need to specify the wave number, you need to specify the omega, and you need to specify the phase. Okay, so usually we need to start off with the initializations for the wave. So you need to prepare the value for k, you need to prepare the values for omega, you need to prepare the values for the amplitude, and then after that you have to prepare the values for lambda, and prepare the values for omega, and then prepare the values for t. So these are all standard things that you need to provide to describe a wave. So what do you start with? For example, you start off with a wavelength, okay, lambda. Now lambda cannot be used in Python because lambda is reserved for, I think, size pi integrate, right? So when you integrate the functions, you need these keywords called lambda, right? So lambda cannot be used. So you have to use, maybe I use lambda. LAMDAA, just to make it to be different from lambda. Right? So if you use lambda, you will run into trouble. So lambda here I refers to the wavelength, and usually I refer to say the wavelength equals to 1. 1 means 1 meter. Now once the wavelength is lambda is defined, then we would define the wave number, which is 2 pi, 2 times pi times pi. So this is 2 pi over lambda. So once once the lambda is defined, then k is defined. So this and this always goes in the pair. The other one is the frequency. So what is the frequency? Frequency is the frequency, right? So let us define a wave which has a frequency of only 1 hertz. So once a 1 hertz frequency is defined, then omega is then also defined. Omega is just np pi. It's a 2 pi over times f, right? Omega is f over 2 pi. Sorry, omega is 2 pi f. Omega, I think there's something wrong, isn't it? Omega is 2 pi over f, 2 pi f. omega, can anyone tell me omega is 2 pi f or f is equals to 2 pi omega? Omega equals to, this wrong. Okay, so I think I have to make a corrections. Wait. Okay, so this is not what I want. Okay. Okay, I think I have to make some corrections here. I'm not supposed to use this file. Make a copy. I'm supposed to work in the copy version, not the original version that you are seeing. Okay, so let me cut and paste this one and restore it. Okay, and then this should not be the case. I think the omega is wrong, being related to frequency. Omega equals to 2 pi f. Okay, omega is equal to 2 pi f. I think this is a more accurate values. Okay, omega is equals to 2 pi f. I think that it looks more correct to me. Omega looks like 2 pi f. Yeah, let me save it. Okay, so I think this is more correct, isn't it? Yeah, because f is 1 over t, so omega is 2 pi over t, so that is correct. So omega is related to the so omega is related to the frequency through a very simple relationship. Omega is 2 pi f. Okay, so this is what it looks like. Omega should be 2 pi f. Here is 2 pi omega f. Omega is 2 pi f. I think this is, I'm going to change it again. Okay, so now it's correct. Omega is 2 pi f. So I have defined omega. Then I need to define my period, right? The period is 1 over f. Now, period is expressed in terms of f. So when you define the frequency and the lambda, then the period omega and k are all fixed. Okay, so I always do that because sometimes I use omega to describe my wave, sometimes I use frequency, sometimes I use angular frequency. So I as well define everything. But basically, if you want to change the frequency of the wavelength, or change the wavelength of the frequency of the wave, or change the wavelength of the wave, then you just change f, you change lambda. But you don't need to change omega, and you don't need to change k, because the k and omega are tied to frequency and lambda. Okay, so that's how you do it. Then you need to provide the amplitude, which is 1. So by doing that, a is defined, k is defined, omega is defined, t is a time, and then you need to define the phi. And usually the phi, for most of our situation, we just ignore the phi, and we set phi equals to 0. It doesn't matter. Okay, so then you can. So the first thing you want to do is to visualize the plot. Okay, so let us plot the functions. But before you plot the function, of course, you always have to define the linear space in which the function have to be displayed. Right? You are simulating a profile of a wave. Then you have to now mention how long you want to simulate the x and how long you want to simulate the t. Now, x is a space dimension, right? So you want to display the whole wave. Then you have to say, okay, what is your x? Right? So you have to study, you have to provide what is the x have to be starting from where to where. Okay, so the x has to begin from NP linear space. they have to begin from somewhere to somewhere, right? So is your time, right? So you want to simulate the time change for the wave and then how long you want to. So it always starts with 0 and up to t last. So you want to simulate for 1 second, 2 seconds, 3 seconds. Then this is the place where you locate the last. So let's just make it 100. Okay, this 100 is just 100. This doesn't really matter that much. Okay. Then what is your XRR? Where you want to start your X and where you want to end. So this is X init and X last. So now I want to tell you again, how do you decide the X init and X last? So again, the X init and X last has to be defined in terms of the dimension of the wave. The characteristic dimension of a wave, right, is given by the wavelength. Right, so wavelength, the wavelength. Okay, so I think this is again an error. I'm sorry about that. Sometimes it just cannot not to make mistakes. So lambda is the wavelength. Lambda is the wavelength. Lambda let me see. I think I saw some mistakes. So lambda is a wave number, and that's not true. Lambda is not a wave number. Lambda is the wavelength, not the wave number. Okay, lambda, the wavelength. Okay, let's save it. Okay, so lambda is the wavelength in unit of meter. Lambda wavelength in units of meter. Yeah, I think that is more correct. Okay, so you have to say how long you want to simulate the size of the wave. So you have to mention the size in unit of lambda. That is what I want to tell you. So you have to specify your x lambda, x last, and y last from here. So you would begin your x init to be how many lambda on the left, and then you have to mention your x last to be how many lambda on the right. Okay, so you always specify lambda. So lambda is d with double A, and this. So the lambda on the left is, say we make it, so we say 3 lambda, 3 lambda maybe, 3 lambda, and then on the right hand side we will simulate it for, so that the whole wave that we're going to see would have a total of 6 wavelengths. Okay, so you want to change it, then you can change it to 2, then you will be a total of negative 2 lambda to the left, negative 2 lambda on the right. Then so is your time, right? Your t init and t last. T init has to, now we'll always begin the simulation with time 0, and then the last values of the frequency of the wave change in time, how many times you want to simulate. You always measure the time of simulation again in the characteristics time scale of the wave, which is period. Okay, so you simulate for how many periods? Say if you want to simulate for 10 periods, you just say 10t. You can change it to be smaller or larger, but you always try to simulate, specify your time in period. In this case, you simulate the length in terms of the length of the size or the spatial size in unit of the wavelength. I think this is very important. Okay, I keep on emphasizing that. So now it's done. So now it would be, then we would be able to plot the wave. Right? Plot PLT. The plot say the wave at XARR and y at XARRT. Now would that work? They may not work. I'm not sure. I think it may not work because in this case the time is not specified. So you have to specify your time. So we specify the time to be 0. This may work, may not work. I think it may not work because the values of y that is defined here has to be a single value. Okay, so if it's an array, then you will run into trouble. So you cannot simulate this. So you have to first generate the ARR, that is the values of y for x in ARR. I think that is how you do it. Okay, so you said y ARR is y simulated at x t for x in x ARR. So that would give you the array of y. Okay, so let's see if this works. Let's print out y ARR. It is a y array. So I see number. No, I see not number because t is not defined. I don't have defined already t. T is 1 over f. So it should be defined, but for some reasons it doesn't define well. 10t. Okay, the reason is because the t is defined before is used before I define the t. So I think it should be like this. Once you have this, then the t has to be defined right after the frequency. Then this is the initial value, and then this is the values of the other parameters. So the sequence of this definition of t matters a lot. Okay, so you cannot use the t before you define it. Just now I used the t before I define it in t last. Okay, so now it works. So yes, so this is the values of the y ARR. So now I'm ready to plot PLT, plot x ARR and y ARR. So I should get a profile that looks like this. Okay, so in order to make things easier, that looks better, normally you would plot horizontal line, axis horizontal line at 0. Okay, so that you see a nice curve here. This happened at t equals to 0. So maybe I should label this as with a plot. So maybe to make things easier, I would like to improve my plot so that I can label it. So what should I do is that I will call this figure ax 0 whatever. I just call it ax equals to subplots like this. I think like this, subplots. If I'm not mistaken, ax subplots. I think PLT. This was learned last lecture, right? Then we have subplots. Then we have an ax plot, and then I think that looks like it. Yeah. So now let me check again. Let me restart it again, and then run it again. Do I get any error? I have no output. I have no output. Okay, kernel is ready. So I think yeah, it is working. So I get nice curve that is plotted. Now I have AX, which is the axis. This axis refers to a frame where the plot is displayed. Okay, so AX is sort of like a frame where I can plot AX ARR and Y ARR. The reason I want to do this is because I want to label it. Okay, so I say AX, I would set values for the title. So the title should be set at what? Title is t equals to plus string. Right? The string is giving me a values of what is the values of t. Now here t is set at 0. Right? So I have a curve that tells me what is the value of t. Now if you change the values of t to say to some other values, say 0.1 times the period, okay, then the period, see, it looks like the wave looks slightly different. Just now it starts from here, but now it looks at different locations. Okay, so it looks like the t would sort of like changes a little bit. Let's say if it's 0.5 t, then the waves now you cannot see quite very clearly how the wave changes with time. But this is obvious that that different values of t you can display the profile. So what we want is to display the profile. But let us try to, before that, let us try to put this into a t loop. For t in something, okay, for t in NP linear space, for 0 to say 2 times the period, and then we have say just say 20 displays, we display for 20 times. People keep coming in. Okay, so I'm going to do here is that I'm going to show this one by one, and then I'm going to plot PLT show. Okay, so this will be a for loop that will display the figure for different t. Okay, so when I press a button, I expect to see a 20 graph to be displayed. T equals to 0, t equals to 1, 2, 3, 4, but only how many? 20, right? So I think it's 20. So let me make it smaller. Okay, so when you make it smaller, you can scroll in this. T equals to 0, t equals to 1, 2, 0.1. So when you make this fast enough, then it looks like the wave is moving. But can you do a better job? Yes, you can do a better job by using the this method. Okay, so let me try now to modify the code again by using this method. I think so I need the display, and I need to prepare the display and then delay, wait, and then clear it. Only then I plot. So what I do here is that I prepare the figure, and then this is to plot the figure. But before I prepare and plot the figure, what should I do is I should do here. So I would first, when I go into the loop, I ask the display to be cleared. That means any display that is displayed, any graph that is displayed before that cleared, and then you wait for a while. Then prepare the display. Okay, it's just like prepare the stage for the graph to be plotted. So by doing that, I would expect the display that you see here in the original graph, it will not be displayed in a separate pictures, but they will all be displayed on the same locations. So it's like overlap on each other. It's like you have the first pictures, then you remove it, you clear it, then you replace it by the second one. Then you wait for a while, then you clear away this picture, then you replace it by the next picture. You wait for a while, then you clear it, then you replace it by the next picture and wait a little bit. So this is what basically the logic looks like to me. Okay, you clear and then you display. So let's try to see if it works. Okay, so I press a button, and if it works, then yeah, I think it works. So now you see that it is actually showing a moving wave that is to the right, because I'm defining the k to be positive. Okay, so you can make the k to be negative if you want to. Then in that case, the k would be negative, then the wave will be moving in the opposite direction. So let me try this. So now to make things better, let me refine the graph a little bit, making it sort of moving for t last. So here the t last only lasts for 10 period. So I should make this, okay, I think here I should make this t last instead of 320 t last. Then I should make this to be 100 as well. Okay, so there will be 100 different frames. So this refers to the frames. Like t equals to 0 is one frame, t equals to 1 delta t, t equals to 2 delta t, t equals to 3 delta t. So it's going to display up to t equals to 100 delta t. So it's going to show you a movie where each frame is different from each other, and there will be a total of 100 frames to be displayed. Then you see the pictures, and this is to print out the values of the t. Okay, so that's how you make the simulation. Now, if you want to make it to reverse in the directions, then you need to make the k to be opposite. And you assign the k explicitly to have a opposite number. Then let's see what happens if you do that. What happened? I just changed this and then run it. I ran it. It doesn't show anything, so I think something is wrong. So normally what happened in this case is that I'll just clear the memory and then make sure that I save my complete file, and then I run it again. Okay, so I'm waiting for this to be created. Okay, so now kernel is restarting. Sometimes it takes a while for the kernel to restart. Now when you see this come out, that means the graph is almost ready. So then you run it again. Then you will be able to see the results. Okay, so now you see the graph, the wave that is propagating to the left. The bad thing about this is that it's keep on flickering, okay? But if you ignore the flickering, then it should look more or less the same, more or less okay. Okay, so you can see that now wave is moving, right? So you can now proudly tell your friend that you know how to simulate a moving wave. You always learn about wave that's moving to the left, to the right in your 103, in your Form 6. But now you can simulate it very easily by just replace the profile of the wave for different t. Now sometimes this is lagging, right? The t has so many different numbers. So let us try to make things better. So this string, let us make this string to have a format that displays only 2 figures instead of displaying like 16 figures in the back. So let us try to do the formatting here. Remember the formatting that we mentioned last time? Let me show you here in case you have already forgotten. So let's say you have say here a t. Now what is a t? T is 10.0. So maybe t equals to 10.0001234. So let us try to print this and then make it into a different format. Say you just want to print out say 10.0, only 3 figures with 1 decimal point. 10.0. So remember what we do? So you have to use this string form. I think 1.2. Say if you want 3, say 3.1. I think let's try it out. Then you have this thing, then you put it into a tuple, then you say this is t, then you make this into a string. I think that is what you do. Okay. Yeah, if I'm not mistaken, I think this should be the case. So that would mean that this is a string to be displayed with a format with a float 3.1, and then inside here is a sign for this, and then this is the values of t. So this is not right. I think something is not wrong. I think it's string 3.1f, f3.1, 3.1f, 3.1f. I think like this. Yeah, I think that is how you look like. So you can convert any string by using this format. So we're going to do that as well. Okay, so I'm going to cut and paste this one, and then I'm going to replace the string by this SCRT with this format. Okay, so let's see. Now I have 3.1, 3.2. So this is a very nice values. So maybe I should put this to be 4, 5, 2 if I want to. But I think more or less it's the same. Okay. It doesn't show up the simulations again. So if I stop it and I interrupt the kernel and then run it over again, then wait for the, yeah, now it's moving. So now it looks like you have a 2 decimal point of t that is displaying. Okay, so now I have finished showing you how to simulate a wave. Now let's move on to the next bit, which is to simulate the other thing, which is to simulate the wave. I think this is a more interesting, well, this is the code I prepared for you, but you can try to run it for. So this is a more comprehensive code in the sense that it is displaying more wave than I do here in the sample. Here I may do, don't know how many waves, 1, 2, 3, 4, 5, then 2 on the left, 2 on the right. So if I make this to be say 4, and then 4 waves on the left and 4 on the right, then there will be a total of 8 waves. So if there's a total of 8 waves, then let's look how it looks like. Restart the kernel and then run it again. Okay, it's taking some time to run it. It's still taking some time to generate the okay, so now it's ready. Okay, so this is very similar to the one that I gave you in the sample. Okay, So this sample that I show in the lab, in the sample code, is more comprehensive, but idea is the same. Okay, I just add in more specificity. I just make the title to be more fancy, and then I add in the x-axis and y-axis, and then you can see this plot the points instead of plotting just a line. Okay, so this is it for the wave simulations. Now, in your assignment that I just prepared for you, I think assignment 10, if I'm not mistaken. Okay, assignment 10, you are supposed to do a simulation for a wave. Okay, so this is a wave simulations. I give you two waves, but in the code here, I only give you one wave. Okay, one wave you can do the simulation quite easily, quite straightforwardly. But in the simulation, I require you to do a simulation for two waves, where two waves is slightly different in their wave number. Right? So one wave, both waves have the same wave number. Okay, so they are the same in the wavelength, but they are slightly different only in the frequency. So you have two waves which is having the same wavelength but slightly different frequency. Then you mix them up. Now what happens is that when you mix them up, you don't say you mix it. You superimpose both waves together. So when you superimpose, then you add y1 to y2. So what happened? So you add y1 and y2 together. So this is a simulation where both y1 and y2 does not add together. So they just move through each other in opposite direction. I think this is another example this is a B, where you have two waves which is slightly different in frequency. They move in the same direction, but if they don't superimpose, then you can see that both waves will travel at different speed, and then they would not moving at the same speed. But if you add them together, you superimpose them, then this is what happened in 3C. Right? So if you have two waves moving in the opposite directions, then you see this oscillation behavior, because at some point both waves will cancel off each other. We call this a destructive interference. Right? But when both waves are added in a constructive manner, then you have a large amplitude. And this is the situation when you have two waves moving opposite to each other and then interfere. And this is what I call a bit phenomena. So you can simulate this bit phenomena and the superimpositions of two waves very easily. Right? So just add them up and then you display them. So this is a very simple task. So you try to do this and you think about it. It's actually not that difficult. Okay. So last time we used add up in the 1.1 class. We have like 1,000 waves with different wavelength add up together. Then what we have is a wave packet. So a wave packet. If you have not only two waves, but say a million or thousands of waves, so you can add up these waves or subtract the wave, make them to be opposite in directions or in the same direction. Then you can see how the wave looks like. Okay, so this is actually quite interesting, especially if you are very curious. All these waves that you learn in 103, you can simulate using this very simple method. Okay, so that is for the wave simulations. So next we are going to simulate the pendulum. Again, it is quite simple, right? So give me the parametric equation for the pendulum, coordinate x and y, then show them on the screen and change your time. Again, when you do this, you have to. Again, when you do that, you have to understand the physics, right? So simulation is okay, it's quite straightforward, it's technically not that difficult. But before you carry out the code writing, you make sure that you understand the mathematics. Right? The mathematics structures of the simulation is more important than the technical process of writing down the code. So first of all, if you want to do a simulation, first you have to know what is the set of parametric equations. So the set of parametric equations is given to you. Now what is important is that you understand that in your in the previous few lectures, I have defined for you how you derive the solution for the second order differential equations that describe a pendulum, right? So it's d2 theta dt squared equals to minus omega squared theta. So that formula has a solution. That solution is this. So this theta equals to theta dot sine omega t plus phi is the solution from the second order differential equations of Newton's law applied to a pendulum. Now you have to import, the most important thing is you have to understand each of the symbol. If you don't understand the meaning of each symbol, then you will not be able to understand the physics. Okay, so theta refers to the angle of the pendulum with respect to the normal. the normal here refers to the vertical line, and this theta is the angle. Okay, the angle changes with time, and the maximum angle that it could displace is theta naught. So the theta naught is the maximum angle it can displace. It's called the amplitude. And then omega is the frequency, which is fixed by the length of the pendulum. If you change the length of the pendulum, then the frequency would change. Like say longer length, then larger, then smaller frequency. If the L is smaller, then the frequency is faster. So the pendulum would oscillate faster. And phase is the angle that would be calculated based on the initial conditions. For example, if you set t equals to 0 and you release it from theta equals to 5 degrees. So then when they set 0 to t, then what happens is that these values of phi has to consistent with angle of 5 degrees. So if this is 0, then I think you can calculate this phi value quite easily. So what I'm trying to say is that at t equals to 0, you specify the values of phi, then you can calculate the theta. Okay, so once you understand how the angle changes with time, then what you want is actually to simulate the pendulum. Right? What you just want to simulate is that the position of the pendulum is described in terms of the xy plane. Right? So you want to simulate on the xy plane. Where is the coordinate x? Where is the coordinate y? But this theta is not coordinate x, coordinate y. You have to translate the polar coordinate into the Cartesian coordinate. So when you simulate, you change x, you change y. So the point can only be calculated or displayed on the screen by the term in terms of x and y. So you have to translate the angle into x and y. So you first refers to the reference point. Before you do any simulation, you must make sure that you know where the where the reference point is. So when I say reference point, that means you have to set up your coordinate system with the origin specified at some location. So in this example, we specify the locations of the origin here. Then along this direction is called the positive direction, y. So this point is y equals 0, and then anywhere which is higher than the 0 is positive y. Then x is defined as the location of the pendulum from the vertical line. So this is how you describe the theta, x and y. So you have to draw the pictures, relate the angle and x and y. This is very important because this is geometry. If the geometry is mixed up and you do not know the geometry and do not know how to write down the equations that relates to geometry, then you will not be able to successfully simulate the variations of the location of the pendulum with respect to time. So you have to understand that given any time t, the angle value is given by this formula. So you generate these values for the theta at different time based on this formula. So you start off with some theta naught, with some phi, and then with some omega. Then with this, then you simulate the theta changes with time. Then for every theta, you convert it into x and convert it into y. Now y is the sort of like the distance from above the coordinate 0, right? So if this is the length of L, then this y is simply given by L minus this part. This part is L cos theta. So L cos theta is just from this point to this point. Right? So the total length is L. From here to here is L. L minus here, L cos theta, will give you this difference of y. So that's how you derive x and y. Now once you are given this current equation, then it becomes quite straightforward. Write a for loop to calculate the values of x and y at different t. And at different t, theta is calculated from theta. At that t, then you translate into x and y. Then you display the point of y and x onto the screen consecutively, changing t. Then you'll be seeing a point that is like rotating. But that would not be optimum, because if you do not make the thing properly, you would have some problems. The problem will be displayed later on when I show you how to do that. Specifically, if you don't fix the frame, right? So if you don't fix the limit of the x and y limit frame, then you would run into trouble. Your simulation would be awkward because the frame would rescale itself. If you don't fix the scale of the frame, that is the limit of x and y, then you see that your frame would be like sometimes large, sometimes small, sometimes large, sometimes small, and sometimes it would not even move at all, even though it's changed in x and y coordinate. Okay, so we will do that in time. We'll come back after say 5 more minutes later, maybe 10, now it's 4:06, so we'll come back at 4:15. Okay, 4:15 is too much. 4:15, yeah, 4:15. So I'll take a break of a few minutes. 4:15, I'll see you again. Okay, bye. Okay, so now we will continue to do this thing. You are still there, right? So it's 4:15 already. Okay, so we want to simulate this. Very easy. You have the coordinate of x and y, so maybe I won't spend that much time. First of all, you have to provide, in order to do this simulation, you have to prepare or initialize the simulation. You have to say, prepare the angle, initial angle, theta naught, and phi and omega. So the omega is described in terms of G over L. So just specify the length L, then omega will be specified because G is a constant. So by specifying the L, there's the length, then omega is specified. You need to specify then the phi and theta. So there are 3 numbers to specify, right? Theta naught, phi, and also L. So you say, okay, this is my theta naught, 5 degree. In the beginning, you release it from 5 degrees. So the pendulum will maximally oscillate with 5 degree. Length is 1 and G is just a constant 9.81. Then omega is expressed as the square root of G over L. Then once that omega is specified, then the period is also specified. Okay, so the x coordinate is just L sine theta, y coordinate is just L times 1 minus sine theta, and theta is the angle, right? So theta changes with time. So initially, primarily the angle is a solution to the second order differentiation of Newton's law. Then theta change with time, then so is x and y would also change. So we want to know what is the coordinate of x and y at different t. Okay, so that is how we do it. So then you have to decide the period of the oscillator, the length, the temporal length where you want to simulate your pendulum. So let us simulate for 5 periods, and then there will be 500 points within this 5 period. Okay, so then again you have to also generate the points between the x and between the y. Okay, so XRR here refers to the values of x theta for t in TARR and y. So TARR, YARR, and XARR, both these 3 things will be used to show the trajectory of the pendulum. Okay, so this is nothing but just a plot that shows you the solutions or how the x and y changes with time. Right, so then I plot the XARR, YARR, and that looks like this. Right? So this is what I expect for a pendulum, right? So the coordinate of x is here, coordinate of y is this. Okay, so at time t equals 0, where is the bob? I think the bob is somewhere here. Okay, on the right hand side where it was 5 degrees. Okay, so very important thing to note is that the x has a scale which is different than the scale of y. Okay, the y scale is very small because when you have a pendulum, the length is like could be quite 1 meter, but when it swings only for 5 degrees. So this cross 5 degrees, and then L is somewhere very high up. Okay, so this is just a small curve with a height of only 0.004 meter. But here, the length of x is much larger than the displacements along the y directions. But anyway, we'll do that. Okay, so the next thing we want to show you is that we want to do a simulation. So you want to change the position of the blob at different time. So how you do that is very simple. So let us start from here. You can actually do this very easily. Let us try to add in this bit. So I need this IPython thing. So I need that into here. So I'm going to modify from this plot and generate the pictures or the videos. Okay, so I need also this thing, right? I need this TARR display thing. Okay, so I need this and this. So what I'm going to do is that I'm going to show for different time, right? So for different time in TARR, I'm going to prepare and clear any existing display, then clear the display, then prepare the display, then do the plot. Okay, so this plot would be this figure, and then this is my plot. So this plot, AX plot is going to be repeated again and again in a T loop. After that, then I'm going to come up from the T loop, and then I'm going to plot show how. Plot show. So this plot show is to be shown after the plot has been done. So I press button, I expect the plot to be shown. But this is not going to be working well because I'm plotting only the XAR. So this is actually going to show me only the same curve as the previous, but this is not what I want. What I want is the point. Okay, I need to show a point of x as a function of t, and then y is a function of t. I think this is what I want to show, right? Not the whole trajectory, but the instantaneous location of the point p, x and t. So this is the x and this is y. So I want to show x and y, but is this going to be correct? No, because x has to be the function of theta, okay, not a function of time. So here the x depends on the values of the angle, but the angle here has a dependence on the time. So if you want to calculate the values of x, you should calculate in terms of theta at the time t. Okay, so that is the more correct way to call the values of y and x at theta. So be careful about this. Okay, so when I press a button, I expect that x on theta will be shown, y at theta t will also be shown at different t. So plot show PLT show, because what happened? Show PLT show, something is wrong with this plot show. There are two plot shows here, so I think that is not right. Okay, so plot show, only one plot show. Line invalid. PLT show. Anyone can help me on that plot show? Why is that the plot show? I think there's not a problem with this plot show. Maybe it's this. Now let me show this first. So I'm doing the troubleshooting now. This is usually the boring part. So I just want to make sure that this gives me the correct output. So theta, x theta, I think that is not true. Okay, so x has to have y have to have this. No, I think there's extra angle. Okay, so now it looks more correct. So I enclose the x and y into a into wrong format. Okay, so I think I fixed this. So there should be y at theta t, x at theta t. Okay, so I think that is now correct. Okay, so do I see any simulations? No, I don't see any simulations for some stupid reasons. So again, we have to stop it, reboot the kernel, and then run it again. So I think the kernel has to be restarted. Okay, so when you start it, then it should be able to generate. Now this is not going to give me a very nice output. The reason is because I have not fixed the frame of the thing. So display clear, and then now nothing come out for some reasons. Let me try to do it again. Run. Is there any output? No. I think this is very common. I always get this problem. I don't know how to fix it also. Okay, let me check my code. It seems to be correct. I think plot show. No, okay. I think it should. I think this plot show should be here. I think this should be here. Okay. So the plot show should be shown within the for loop, not outside the for loop. So this is to display point by point the coordinate of x and y at different t. Coming out? No, it didn't come out. Wait, let's just wait again. Restart the kernel. Then run over again. Stop this. Interrupt the kernel, and then run over again. Okay, it's connected. Is it right? Yeah, it's running, so it has run, and then I want to show the simulations. It takes some time for the simulation to be shown. What is different with XAR and XAR? Okay, so the question is let me explain again. XAR is the coordinate of x that is dependent on theta at different t. So t is what we call the parameter t. So t changes like monotonously. So when t change, theta change. When theta change, x change. So you learn in the ZCE 110 function of a function, right? So theta is dependent on t and x is dependent on theta. So XARR is generated for different theta, where theta is generated for different t. So in principle, the x, when you want to call the x, you should have to call the x as a function of theta, whereas theta has to be a function of t. Okay, so it's sort of like cascaded dependence. But why don't you see my output? Okay, the output is here. So now you see this, it doesn't look like it. The reason is because it keeps on changing. There's something is showing, but you don't see it. The reason is because when I plot it, I didn't ask it to plot a point, right? So I just plot x and t. I should ask it to plot a point, right? Like this. Then only it will plot the point. So again, I don't know where the simulation wrong. I just press the run, save it. It doesn't show up. Simulations. Try again. Run it again. So I'm waiting for the simulation to show up. If it doesn't show up, then I have to drop and restart the kernel. Then run again. Wait for the kernel to restart. Run again. Now, if anyone can help me on why is that I keep on sometimes the simulation doesn't appear. Maybe I need time. Yeah. So now it is restarting. Please wait. So I'm waiting patiently. I hope that when it restarted, then things will run well. Okay. Still waiting. Still waiting. So when it finish, I expect that you will see a point moving, but the oscillations of the point would not be nice. It would be, you'll see later on yourself. It doesn't restart. It takes forever. Okay, now you have restarted. Okay, so if restarted, in order to see again, I have to run it again. Okay, run. Okay, yeah. So let me run again. Run. Okay, so you see that the point is shown, but the scale of the frame is keep on changing. Right? So the point is actually changing in time, but when it changes in time, the default display is that whatever printed has to be fixed in the middle of the frame. So what you have to do is that you have to fix the range of the frame. So you have to fix the x to be from, say, between minus something to plus something. You have to fix your y to be from 0 to something. Or else, if you don't fix it well, then that is what you get. Okay, so to fix the problem, you have to fix the frame. Okay, so let us try to fix the frame. So you have to fix the frame by using a command. Okay, so there's a command which is very important called the fix the frame. So I think this is the command set limit. Okay, so I have to fix it by plot x limit and y limit. So here you see that the simulation says the x is changing from left to right. Okay, so it's from left to right. What is the most left value? The most left value is when sine theta equals to sine negative theta dot times L. and the most right hand side values of x is when theta is equals to theta dot. So the x left is set to be L sine theta dot with a minus sign in the theta, and then x right to be L sine theta dot. So I would like to fix the axis by using this method. I want to plot ALP. I will fix the limit of for x to have a value of x left and f right to be value of x right. Now what is x left and x right? I'm going to declare my x left and x right here. F left should be a value which is equals to 1. Now there are different ways how you do that, okay? So I would say this to be L times NP sine negative times theta dot. Then the x right is this value. Okay, and it should be positive. So this makes sense to me because I know that x is always oscillating from this point to that point. Now the other way to define the x left, x right is to look at the XARR. You see, XARR is a value. Let me show it here. Okay, so let me open it. And so this XARR is an array. So let me print it out. Print out the X array. For some reason it doesn't print out because of these things here. Okay, maybe I just okay, anyway, what XARR is an array. So the minimum of XARR is the x left, right? The maximum of XARR is the x right. So you can also change your XARR. You can extract the x left as alternatively to be a value of NP minimum of XARR. I think this is one possible way. Both will give you the same answer. Okay, all this will give you the max of XARR. So either way. So now I have fixed my XARR. So let me stop it. Then this is XARR. Okay, so this XARR. So if you can do that, you can say NP min and NP dot min minimum of XARR will give you this number. This will be your x left. Then if you say is max, x max, then it gives you a max right. So okay. Now the same thing you can also do it for L, but it would not be good to do it L in this manner. But anyway, we have to fix the left limit, right? Limit for y and for x as well. So now we have fixed the limit of the x-axis to be shown, so that the x-axis will be fixed. It would not change in its range. So let me run it again. I'm not sure whether this will work. Okay, so now it looks like it's working. The x-axis that my mouse show here is fixed. It's from minus L x left here. Is the x right here. So you see that the pendulum is actually changing, but the y value is keep on changing as well. X is fixed, but y is not. So now we have to fix the value of L of y. So in order to see the whole picture like this, then you know that the y starts from 0 and then it all the way up to L. So you want to fix the x y minimum to be 0, y maximum to be L. But I wouldn't call this y f left, f right. I'm going to call this y low. I'm going to call this y high. So y low, y high would be L. So that is what you expect, but that would not be good as well. I'll show you why. So let us plot, fix the y limit to be y low. This is the limit for y low and y high. So by doing this plot limit, you fix the axis range. Then all the point that is displayed inside the frame would have a fixed frame. Then you will see the effects of the ball to change in time. Okay, so I have to interrupt it and then restart over again and save it and then run it over again. Okay, so this is okay, so it's restarting. It takes forever. Well, anyway, I think this will be working. So it's working. No, it is still restarting. Now, when you see this later on, you find that the result will not be satisfactory. The reason is because the y is too large. The axis x and y also are not set to be at the same scale. Now, I'm showing you all the trouble with this simulation, but I'm going to improve this step by step, right? So if you don't fix the x and y limit, then we see that the ball will not move. But when we fix this x and y, then you will see that the frame is fixed. Then the ball will start to move as well, but like this. But this effect is not good because it has two problems. Okay. Because the y is just like from 0 to 1, so it's 1 meter, but the x is from -8 to 8. So obviously the scale of the x and y are not the same, right? So you have to first fix the scale of x and y so that they are proportional to each other, right? So the scale have to be fixed to be the same. You know what I mean by the scale? Like when you draw a graph paper, like you always fix the scale 1 to 5, 1 to 10, right? So the scale for x is obviously representing a more, well, the scale is not the same. So now we're going to fix the scale. So that is how to fix the scale. To fix the scale of x and y, to make them to be the same, you need this command called set expect to be equal. So when you set the expect to be equal, then whatever that is shown for the ax naught, right? So you have to set the axis for the frame ax naught to be the same, right? So this is what I'm going to do now. I'm going to fix it. So what you see is that when you fix it, the length of y to be longer, and then the length of x will be very small because now the scale of x and y become the same. So what happened? Run it. When I run it, then it doesn't show. So again, I have to restart the kernel and then run it over again. Okay, so then wait patiently again. So this is the bad thing about the simulation using Python. It's always been delaying. Okay, so it looks like there's something coming out. It's starting. Can I press this again? Let me try to press this again. No, it doesn't work. Back. You stop it. Then run it over again. Now it's running. So now you see that the x-axis now has the same scale as this, right? But it is moving very slowly. Okay. So you want to make the simulation to look better. Try to refine it. For example, make the box to be displayed for more. Well, what I mean is that you can make the x limit to be slightly larger and to make the low limit to be slightly lower. So the left, you make the left to be slightly less. So you make it to be saying, let's say 0.1 times, 0.1 times left, x left, right? So that would somehow shift the left limit a little bit by 10%. Then on the right hand side, you add it to be 0.1 times x, right? So that would make the range of x to be slightly wider. So same thing here, you make the y naught to be slightly less than 0.1. Maybe this is, I'll just fix the y to be the same. So that will make the y to be smaller a little bit. Then hopefully that it will look better now. Now again, when I press the button, I lost my simulations. So I have to stop it and then run it over again, interrupting kernel, run over again. Okay, now I see this. Now it looks better, right? So the y low is sort of like displays a little bit lower, and then the x is also displays wider as well, and you can see the simulation running. So that is okay, but still not satisfactory. What you want is to have this kind of thing, right? So you want to have For example, this simulation, you want to add in the trajectory of simulations, and then you plot it, and then somehow you don't show for the full length. Sometimes you can make it to be shorter as well. So maybe you don't make the Y max to be L, or no, Y max, the L, the Y naught, not to make it full length, so maybe half of it will do. So by doing that, then you can sort of like zoom in a little bit. So I'm showing you that you can actually zoom in to the simulation by rescaling the frame range. Okay, so stop it and then run it over again. Okay, so now you see that this is not a height of 1 but half of L. So that allows you to zoom in a little bit. Now you can so far what I have done is that by fixing the left right of x, so this is f left x right, changing the values of f left x right, and y low y high would fix the size of the frame where you display the simulation. You can make the size of the frame to be wider or smaller. So to adjust, you have to learn how to adjust this sort of frame dynamically. If the simulation doesn't appear to be working very well, then you have to adjust it. If you don't adjust it, then it looks weird. Then the second thing is that you make sure that you have to fix, of course, fixing the limit of x and y is one important thing. Second thing is that you sometimes have to fix the ratio of the x and y axis. Only then it looks good. So the next thing is that you want to say plot overlap on it, the trajectory of the pendulum, so that it guides your visual thing, right? So you guide your. So what you do is that instead of showing this, then you plot one more thing, to plot XARR and YARR. So that YARR will give you the full trajectory that overlaps onto the trajectory of the pendulum. Okay, so now you see this. Right, so you just add in this one just to guide your visual so that you see that this bob is indeed moving along this line, but still the curvature doesn't look like it is really that curved. It looks like it's a straight because the x displacement is much smaller than the y displacement. If you want to see the curvature to be really curved, then you have to further zoom in to say, instead of plotting now the length to be 0.5L, you need it to be smaller, say just 0.2L will do. Then you interrupt it and then you run it. So now it looks much better, right? So the curve looks more curved than previous. Then the next thing is that you want to draw a line, right? To draw a line that would link up. You want to draw a line to link up the bulb and the pivotal point, right? So then you will be able to see this line is changing with time. Right? So here we only simulate the bulb, right? The bulb that is changing. So how do you draw the line? Now to draw a line, you need to learn this very simple thing. So here I have a very simple code that says you have 2 points. For example, you have the first point, P1 and P2. So the P1 is, I think, this one with a coordinate of 0, 0. And then P2 is at the coordinate of 3, 4. This is 3, this is 4, this is coordinate. How do you draw the line between them? I think the idea is very simple. Well, it's like this. So you collect the x coordinate of both points into XCL. Then you collect the y coordinate of both points on another variable called YCL. So YCL then is the set of the y coordinate of these 2 points P1, P2, and XCL is the set containing 2 x coordinate of the point P1, P2. Then you just plot XCL, YCL. I think CL here stands for, XCL stands for collections or something like that. I'll just give it a name. So now we have a ball, right? So this ball is having the coordinate of x and y. And then the other point, if you want to draw a line connecting this point, then you have to know the other line. But the other line is sitting here. So this is what we call a pivotal point. So the pivot point is having a location which is at some value, right? You have to know where is the coordinate for the pivot point. So here x is 0. The pivot point has a y coordinate of L. So here, in order to plot the line, let me try this. Okay, so in order to plot the line, let me call a pivot point. Now the pivot point is a coordinate which is at 0 and L. Okay, then I want to draw a line. So to draw a line according to this exercise is simply this, right? So you have to construct the collections of the 2 points. Okay, so I'm going to construct the collection. So this is the x coordinate of the pivot point. So 0 is the x coordinate of the pivot point. Y is the coordinate of y for the pivot point. The other point is this. Maybe I should just connect this here. Okay, so here I have x and y theta. Okay, so I need to put this x theta t and 0 in one group, and I have to put the L and y theta in another group. Okay, so let me show you here. So I call this, or don't know what I call this, XCL to be two number. The first number is the 0 component of pivotal point, and the second component is the x theta. Okay, x theta with a function of t. So that gives me the x coordinate of the pivot point and the x coordinate. So now I need another collections of y, so which is pivotal 1, and this should be y. Right. So I would then connect the XCL and YCL using this method. So I just need this. So this plot XCL YCL would connect them together. Will connect these 2 points together, XCL and YCL together. So I'll call this this is a line. Okay, a line. So the line is constructed based on this 4 things. So I hope that this will work. Okay, so this will plot me a line connecting the pivot point and the ball. So let's see if this is working. Let me stop this and then run it again. Okay, now I see, yes, I see something is happening. So you see it is working, it is moving. So I have a line that is moving. So, but I only displays the y up to 0.2 L. So let me change it to see the picture, the whole picture. Maybe I just make this to become just full L. Run it, stop it, and then run it. Okay, now it looks much better. Okay, so you have this line moving around like this, but can you make it better? Yes, you can make it better by displaying the vertical line. So let us try to display a vertical line. The vertical line should be displayed very easily by having another plot here called PLT. No, I think it's PLT dot axis vertical line at 0. Right, vertical line at 0 will give you a vertical line that goes through the middle of the simulations. So I'll stop it and then run it again. What happened? Okay, here. So stop it and then run it again. Okay, so now you see a vertical line has been displayed. Right, so now we have a simulations of a pendulum. The imperfection of this is that it's keep on flickering. I think it's flickering because of the RAM problem. The RAM does not fast enough. But basically, this is how you do the simulation. Okay, so you see the trajectory in green color, then you see the vertical line, and then you see the whole thing is moving. So that's how you simulate. So the idea here is that you have to make sure that you have the formula for the this one. No, this is not the one that I'm talking about. Is this a 1? Yeah, I think, yeah, this is the one that I'm simulating. Okay, so now you learn the principle. Give me the x and y coordinate as a function of time. Then you put them into a for loop, and then you define the time space. Then you switch on these two display lines. You fix the frame. At some time you need to make the x and y coordinate to be equal. Then you add in other cosmetic, for example, the vertical line. And then if you want a line, then this is how you do a line. You have to construct a line yourself. In order to do so, you need to know where the coordinate is. Okay, if you do not know where the coordinate is, you do not know the geometry, you cannot write down the geometry of the systems in terms of formula, then you will not be able to simulate correctly. Okay. Now this is particularly important if you go to the last sample. Now in this particular last sample, in order to simulate this problem of a circle with a triangle inside a side of L, you need to know geometry, right? So this geometry is what you learn in Form 3, right? So you have a circle with length whatever r, with radius r, with a side encrypt inside the circle L, right? So this is a length of triangle, and then you have a circle which is given by r. So you are asked to simulate how this triangle is rotating inside the circle, where this 3 point is moving along. Now, in order to do that simulation, geometry is very important. So in my class, not only you need to know how to do the simulations using Python, it is almost mandatory, or more importantly, you need to know the equation. You need to know your math. You need to know how to write down the mathematics that describes the problem. Now, I think this is much more difficult than writing the code itself. Okay, so if your math is not good, then you will not be able to even start it. So, for example, in this case, if you want to rotate an equal triangle with side L inside a circle, first of all, you just draw it on the paper. Then you choose the point 0, 0 here as your reference origin. Then this is a circle. Then you label the circle has a length of r. You see this cursor showing that the length of r is here. Then the side has a length of L. Right? The length of L and the r are related. Right? So they are very easily related. And then you have to know also the angle. Right? So if this is an equal angle, then is an equal triangle, then the angle must be easily calculated. For example, this angle here is 360 divided by 3, because you have 3 sectors, I have 3 points, so this angle is 360. And then you can relate the radius of r and the length of L using what I call Cosine Theorem. Right? The Cosine Theorem relates the L square and the length r. Yeah, this is the length of r. This is the length of r. So L square is r square plus r square plus r square times this angle. This angle is 120. So this is the cosine theorem that you write down. Then you will be able to relate the L and R. So in these questions, once you are given L, you will be able to calculate R. Or if you are given R, you'll be able to calculate L for this angle. The angle has 3 points, so I label this n as 3. 1, 2, 3. 3 points, you have n equals to 3. So if it's 4 points, then it becomes a square inscribed inside a circle. Okay, so now once you have written or drawn the geometry, then you need to know how to assign the coordinates, right? So you need to know what is the coordinate of this point, what is the coordinate of this point, what is the coordinate of this point. So once you have written down the coordinate, then you have to know that you are going to make a rotation. In order to make these rotations, the best way to describe rotation is in polar coordinate, not in x and y coordinate. XY coordinate is what we call a Cartesian coordinate. It is used for system where it has this rectangular symmetry. Like for example, projectile motion. Projectile motion is naturally described in x and y coordinate because it has this rectangular, that is, it has translational symmetry along x, it has translational symmetry along the y. But for rotations, x and y is not really suitable. You need to use the coordinate system r and theta, the polar coordinate system. So in physics, you learn many different coordinate systems. Like you learn at least three types of coordinate system: the rectangular coordinate system, or you call it Euclidean geometry system, x and y and z. Then you learn the polar coordinate system, this is r and theta. So the generalizations of polar coordinate system is spherical coordinate system, r, theta, and phi. Then you also learn this cylindrical coordinate system, r, phi, whatever. So you have all these different coordinate system, and for different types of problem, you use different type of coordinate systems. Okay, so for rotations, you use polar coordinate system. So you have to know how to describe the rotations of these 3 points in the coordinate system, in the polar coordinate system. Once you can do that, then you'll be able to translate that questions into formula that is theta, angle of x in terms of, well, let me say it again here. So you need to write down this formula, like the x, a, x, b, x, c, y, a, y, b, y, c. Both these are describing the x, y, z, x and y coordinate for these 3 points. So I call this point number 1, point number 2, point number 3, or point A, point B, point C. So the coordinate of point A is given by x, a, y, a, and you have to then translate the x, a, and y, a into the form of polar coordinates. So x, a, y, a will then be translated into r and theta. Right? R, A, and theta. Now, since this is a circle, and all the points of the triangle are located on the circle, then the distance of the point from the center R is constant. Right? So if you have a point described with x and y is changing. So you have two variables that change with time. But if you describe the point in terms of polar coordinate, then only the angle change with time, but the radius is constant. So that would somehow simplify your description, because instead of having two variables, you have only one variable, which is the theta. Right? Then theta changes with time and is rotating. So you know that the angle changes with time through this very simple formula. So you have to fix a rotational rate, omega, which is a rotational symmetry, a rotational angle, rotational speed. So you learn this in Form 6, and you not only have this translational velocity v, you also have the rotational velocity omega, which is defined as 2 pi over t. T is the period. So you assume there is a rotational speed omega. You fix the numbers. Omega is say 0.1 radian per second or whatever. Then when this thing is rotating, then the angle of any point at the next time steps t plus delta t will be just equals to the values of the original angle at time t plus the rotational speed times the displacement in time. Okay, so omega times delta t is the slight displacement in angle within time delta t. So that is how you describe the rotations effects of an object. So once you have everything in place, then it will be easy for you to do the simulation. So you just fix the coordinate of A, B, C initially. Then you calculate what is the theta A, theta B, theta C at time 0. Then you display the point xa, xb, xc at t goes to 0. Then you have a for loop. Then the for loop will run for I equals to say 1 delta t, 2 delta t, 3 delta t, 4 delta t. For each delta t, you calculate the next value of the angle. Then you displace the points of these three points on the t. Then you display it, and you display it into a forms of a video. Okay, so then you'll be able to simulate this. So these are all the very simple tricks that I show here. Now in your assignment, I think the assignment number 10, one of the assignment is to do this. Is this how to do it? No, not in your assignment, in your mini project. In your mini project, you are asked to simulate a moving object which is in 3D. In 3D, now in 3D, 2D, 1D, 2D. So which is in 3D. So in 3D is more complicated, but the 2D simulations is not as difficult. So this is a still 2D simulation. You need to know how the equation looks like. You need to formulate the formula and then translate into this code. Okay, so 2D, if you know how to do it, then you'll be able to do it in 3D. So mini project offer one of the opportunity for you to simulate a moving, a rotating triangle, not triangle, a moving pyramids, which will oscillate in size, which is much more complicated than this. Okay, so we don't have much time. We have this example which I have not explained to you, which is on a simulation of a box of particles where it collides and then bounces off with the box. But we will do this later on when you come back from holidays. So I think the assignment 10 could be more than what you can consume. So what I'm going to do here is that I'm going to take away question 1. I'm going to take away question 2 because maybe you have not ready yet. But I think question 3 you'll be able to do it, okay, because I have already discussed it in today's lecture. So I'm going to put questions 1 and question 2 in assignment 11. Okay, so assignment 10 will only comprise of one question, so you can do it during the holiday. But I expect to have you to come back after the Raya break. We have a test. So what kind of test would that be? I have not figured out yet, but probably will be something on simulation. Okay, so I'll give you some simulations, then you just do it within 1 or 2 hours, if I'm not sure, maybe 1 hour. That will be constitute a second test. So most likely second, when you come back after 1 week of your Raya holiday on Friday. So we'll make a test on Friday. Okay, so that you'll be more prepared. I think we still have a little bit of time. So Friday we have a test on simulation. So that on next week, not next week, when you come back from Raya holiday on Tuesday, we will have some more time to go through these 2 exercises and also the discussion of this example. But if you have time during your Raya holiday and you are now at MCO at your home, you have nothing to do, you may as well read and go through this simulation yourself, try to understand it. But when you come back, you're going to go through this again so that you can do the simulations on question 1 and question 2 on the simulation of a box of particles. So you are going to ask to do this kind of simulation for some problem. It doesn't work for some reason. I don't know why, but it doesn't matter. Okay. So now before you go off, I just want to remind every one of you, there is already a project list. So for those who have not checked on the project list, would you please take a look at the project list. You are going to pick one next week. So I'm going to open up a Google form. You just fill in your preference. There will be like 20 questions. So you have 4 weeks to complete one of these. You just need to complete one. Say you want this. So this is hypercolloid. I don't know what it is. It's a kind of simulations. Now after the discussion of today and probably next lecture, you will be able to simulate this kind of thing. So you have this kind of ball, circle, then you have this thing. Then you are supposed to now show this trajectory and simulate it. So these are the mini projects. They are complicated one, they are simple one, but most of these are not as simple. Okay, the simplest one, there's only one, but only 1 or 2 persons have the chance to choose the simplest one. Most people would have to force to choose those that is difficult. Okay, so there are physics questions, there are simulation questions. These are simulation questions, are physics, very physics questions, and also machine learning project. Last year was offered, but no one taking up these 2 last. And then this is the one that I designed myself. A coronavirus thing. So your job is to this is a test 1 question. It's an extension of test 1 questions, slightly more complicated but not as complicated. So these are all the examples that you could pick up, but you have not make the choice at the moment next week. So when I'm ready, I'll announce it so that everyone can go online and then pick. Once 1 question or 1 project has been picked up or chosen by 1 group, then you cannot choose it anymore. You have to first come first serve. 2 people will be forming 1 group. Okay, so you have to find a partner so that both of you will work together. Okay, so all the instruction has been clearly stated here. Read through the instruction here. Don't ask me too much. If you don't understand, only then you ask me. But you should be able to follow the instruction. I think the instruction is very clear cut. So follow the instructions, then pick one and then submit it. I'll give you an example of a sample of how to do the report. And also the marks how I grade it also, the rubric has also been specified very clearly on the screen here. Okay, so that's all for today. So I wish those who are celebrating Raya, Selamat Hari Raya. I'll come back next 2 weeks later. Any questions before we dismiss for this class today? Any other questions from anyone? No? Okay, so you all have one question for the assignment, and so try to go through the list. So that's all for today. So I'm happy that you are still with me. Many of you are not, but some of you are still with me. Okay, so that's all for today. Thank you very much.